September 2023, Pratt & Whitney sent a letter to the airlines that operated its PW1100 geared turbofan engine, the engine that powers half of all Airbus A320neo family aircraft in service worldwide. The letter disclosed that a manufacturing defect had been identified in a critical turbine component. The defect was microscopic, a contamination in the metal powder used to forge the high-pressure turbine disc. Introduced during the manufacturing process at a supplier's facility, the contaminated disc, under the extreme temperatures and rotational loads of jet engine operation, could develop cracks significantly faster than design expectations. If those cracks propagated undetected, the disc could fail. An uncontained turbine disc failure at cruise speed and altitude is one of the worst things that can happen to a commercial aircraft in flight. Within weeks of the letter, airlines were pulling aircraft from service for mandatory inspections. Not dozens, not a few hundred. By the end of 2023, analysts estimated that between 600 and 900 aircraft, up to 1/4 of the global A320neo fleet, were either grounded or operating on severely restricted inspection schedules that made normal commercial operation impossible. The total economic damage, when including the cost of inspections, spare engine shortages, wet lease replacements, and capacity disruptions, was being estimated in the range of $6 to $8 billion globally. But here is the detail that made the situation genuinely alarming. This was not the beginning of the problem. This was the point at which Pratt & Whitney stopped being able to manage it quietly. The PW1100G, commonly referred to as the Geared Turbofan, or GTF, represented one of the most significant engineering advances in commercial aviation in a generation. Traditional turbofan engines operate with the fan at the front of the engine, spinning at the same rotational speed as the low-pressure turbine stages at the rear. This creates a design compromise. The fan wants to spin slowly for efficiency, while the turbine stages want to spin fast for power. For decades, engine designers managed this compromise by accepting that neither component could operate at its ideal speed. Pratt & Whitney's innovation was to introduce a gearbox between the fan and the turbine, allowing each to spin at its own optimal speed independently. The fan could rotate roughly 3 times slower than the low-pressure turbine, dramatically improving efficiency at both ends. The fuel savings were substantial. Airlines operating PW10E/G powered A320neos reported fuel burn improvements of 15 to 20% compared to equivalent aircraft with older engine types. In an industry where fuel represents 20 to 30% of operating costs, those savings were the difference between profitable and unprofitable routes. When Airbus launched the A320neo program in Lausanne-Liège, Pratt & Whitney competed against CFM's LEAP engine for the right to power half the world's most popular commercial aircraft. Both were selected, offering airlines a choice. Pratt & Whitney won roughly half the A320neo market, hundreds of aircraft worth tens of billions of dollars in engine contracts and long-term maintenance agreements. It was the most important commercial engine program in the company's history. The contamination problem that surfaced in 2023 originated years earlier. During the manufacturing scale-up that accompanied the A320neo's entry into service in Lausanne-Liège, as production ramped to meet the extraordinary demand from airlines ordering the new aircraft, Pratt & Whitney's powder metal supply chain came under pressure. Powder metallurgy, the process of forming high-precision components from metallic powder that is compressed, sintered, and machined, requires exacting control of the powder composition and purity. The high-pressure turbine disc, which operates at temperatures approaching the melting point of nickel superalloys and rotational speeds exceeding 20,000 revolutions per minute, is among the most demanding components in any jet engine. Its integrity is not optional. It is absolute. At some point, during the accelerated manufacturing period, a batch of powder was introduced that did not meet the required purity specifications. The contamination was not visible in finished components. Standard non-destructive testing did not flag it. The discs were certified, installed, and put into service aboard aircraft flying hundreds of thousands of revenue passengers. The contamination was only identified years later through advanced materials analysis that was not part of the original manufacturing quality protocol. Once identified, The challenge was not simple. Pratt and Whitney could not immediately tell regulators which specific engines had been built with contaminated discs and which had not. The manufacturing records were insufficiently granular to isolate the affected production window with certainty. The result was that a broad range of engines, far more than the number actually containing contaminated material, had to be treated as potentially affected. The inspection burden fell on all of them. The cascading effect on airline operations was severe and immediate. Indigo, India's largest carrier by market share, grounded 30 aircraft in late 2023, roughly 10% of its fleet, pending inspections. Go Air, another Indian budget carrier, had already collapsed, partly due to the engine issues, reducing its flyable fleet below viable operational minimums. Air Asia and Frontier Airlines in the United States each grounded multiple aircraft. Wizz Air, the Hungarian ultra-low-cost carrier that had bet heavily on a Neo family aircraft, disclosed that the engine inspections were reducing its available fleet by 40 to 50 aircraft at times, forcing it to wet lease replacement aircraft at rates of $300,000 to $400,000 per aircraft per month. The wet lease market, which is the mechanism by which airlines temporarily lease aircraft, including crew and maintenance, from other carriers, saw demand spike in ways it had not since the COVID-19 pandemic. Airlines that needed to replace grounded capacity discovered that there were not enough spare wide-body or narrow-body aircraft available for lease, because every airline in the Neo network was competing for the same limited pool of temporary capacity simultaneously. Lease rates that had averaged $150,000 per aircraft per month in early 2023 climbed to $400,000 or higher for some aircraft types by the end of the year. The inspection program that Pratt and Whitney designed in response to the disclosure required borescope inspections of the high-pressure turbine at intervals far shorter than normal. Some aircraft required inspections after every 200 flight cycles, a number that a high-utilization narrow-body aircraft can achieve in roughly a month. Each inspection required the engine to be partially disassembled, examined by a qualified technician with specialized equipment, and reassembled before the aircraft could return to service. The inspection itself took between 24 and 48 hours per engine, and each aircraft has 2 engines. Airlines running 15 aircraft that all required inspections simultaneously faced the prospect of having their entire maintenance workforce fully consumed by this single task. Pratt and Whitney committed to providing replacement engines to allow airlines to maintain operations while affected engines were inspected, but the pool of spare engines was not large enough to meet the simultaneous demand from all affected carriers. Engine leasing rates surged. Airlines that could not access spare engines simply grounded aircraft and absorbed the revenue loss. By early 2024, the problem was not resolving on the timelines Pratt and Whitney had initially suggested. New analysis was extending the estimated duration of the inspection campaign. Airlines that had been told affected engines would be cleared or replaced within months were being told to plan for years. The total number of aircraft expected to experience operational disruption due to the inspection program grew, not shrank, as the campaign progressed. The financial toll was beginning to reach the scale of the estimate. Pratt & Whitney's parent company, RTX, disclosed charges of $3 billion related to the engine issues in 2023 alone, with additional charges anticipated. Airlines across Europe, Asia, and North America had collectively disclosed hundreds of millions of dollars in capacity losses attributable to the groundings. The capacity crunch contributed to elevated airfares across multiple markets, as airlines reduced schedules and passengers competed for fewer available seats. The MRO network's inability to keep pace with demand introduced a secondary crisis that will outlast the primary inspection campaign. When an airline removes an engine from service for a mandatory inspection and ships it to a qualified MRO facility, the expectation is that the facility will complete the work within a defined window, typically 60 to 90 days, and return a serviceable engine. During the PW1100G crisis, that window extended to 180 days, then 270 days. For some operators, airlines that had submitted engines in the third quarter of 2023 were still waiting for them in the second quarter of 2024. This created a cascading problem. Airlines needed replacement engines to operate the aircraft that had had engines removed, but the pool of serviceable spare engines was itself being drawn down to fill these temporary needs, and those spare engines were also subject to inspection requirements. The global spare engine pool for the AI Arsenio family shrank faster than Pratt & Whitney could clear inspections, and the airlines most dependent on the A. Arsenio, precisely the budget carriers with no alternative fleet, had the least ability to manage the gap. Pratt & Whitney's capacity expansion plans called for adding MRO capability through partnerships with existing facilities and through investment in expanded shop capacity at its own network. The company contracted with MRO providers in Singapore, Belgium, and Canada to process additional engines outside its primary facilities. Progress was real but insufficient. The inspection queue remained backlogged through the first half of 2024, and projections for full fleet clearance continued to be revised toward later dates. The airlines waiting for their engines had little recourse, except to wet lease substitute aircraft at rates that reflected the broader shortage itself, inflated by the same crisis they were suffering from. Pratt & Whitney built an engine so advanced that it changed the economics of commercial aviation. The geared turbofan eliminated a compromise that engineers had been managing for 50 years. It delivered fuel savings that made routes viable that weren't viable before. And then, a contamination in a metal powder, invisible, unmeasurable in the original quality process, introduced during the frenetic ramp-up of production, found its way into the critical, rotating component of an engine operating at the absolute frontier of material science. The investigation, the inspections, and the replacement program will eventually resolve the crisis, but the lesson will take longer to fully digest. The more precisely engineered a system becomes, the more precisely controlled its manufacturing must be, and precision manufacturing at scale, under the commercial pressure of the world's most competitive aircraft program, is not always precise enough. The industry that built the geared turbofan, a genuine engineering triumph, now has to reckon with the fact that its manufacturing supply chain was not built to the same standard of precision as the engine it was producing. That gap between engineering ambition and manufacturing discipline is the real engine problem. The discontamination